Good morning, students, and welcome to the another session of Structural Analysis 2. I'm sure that you are doing well and hopefully practicing also regarding the concepts of the structural analysis. What we have been discussing since last many lectures. We are discussing on the energy principles basically. So, it is important to go through a short and quick recollection. In the last session, we have seen and how to apply energy principles for beam analysis, and we have reached to the application of the second energy principle of Castigliano. We have been using it for analysis of the beams, which are largely indeterminate. Today, if time permits, we'll go with the further application and extension of the Castigliano's second energy principle for truss analysis. And before that, I would like to share one numerical with you, which you need to completely obtain and work upon, because I want to check the progress also. So I will be sharing one problem, which is a bent cantilever with all of you, where you need to require to calculate the reaction of the support in the bent cantilever with the help of second energy principle by using the very typical and old well-known equation like this. First we'll practice on this, and then I will show you how to use this particular equation. So today everyone has to work along with me, because you will be primarily working on, I will be sitting back, I'll be waiting for your answers, and I need answer from any one of you, so I will be randomly asking the answers. So again, I'll give you few minutes. You all please bring your writing tools with you, calculators, some notes, some pens, and everything should be with you, so that you can relate yourself. And that's why I'm repeating a little bit of the old knowledge and information that already we have shared earlier in the previous sessions, so that you can recall, right? So here, this is what we have used in the consecutive few last sessions, where we have primarily utilized energy principle number one for displacements and rotation calculation, and we have sufficiently made practice over it, and then we started actually the calculations of the complex problems. As one of the problem you can see here, it's a combination of UDL and point load on cantilever. And then we started discussion on second energy principle application, and that actually helped us to calculate the reactions. So now you know that energy principle number one is primarily for deformation calculation or displacement calculation, and energy principle number two is useful to obtain reactions of indeterminate structures with extraordinary ease and comfort, right? So that is what we have seen in the last few sessions, I would say, where uh, I think this was the last numerical that we have already discussed. Yes, I have solved it for you. You can see here, if you wish, you can recall that what is the process actually. The process is very simple. While using the calculation, second energy principle for analysis of beams, for the reaction purpose, what you have to do is you have to consider reaction at a particular joint as it is, and develop your generalized moment equation. You can see here that we have considered VC here, right? Reaction at C, and we have included VC in our equation itself, so that with respect to that, here you can see, with respect to that, we can take a partial derivative of our generalized moment equation, and later on you can integrate it according to the available segmental length, right? So that is what is desirable. And now we'll progress with some more practice. Now you have to practice it on, I think in last class, here we can see that This we have discussed already that we will be practicing on bent cantilever. So today I would like to give you one numerical on bent cantilever, and then we'll go for analysis of this type of indeterminate trusses. Now, before we go for the truss analysis, I would like to discuss here is why we need to use energy principle number 2 in truss analysis, because the principle number 2 is largely related with the total energy stored in the structure, and with the respect of particular type of reaction or internal forces. Let us say this is a reaction which is desirable, or let us say I want to calculate any internal member force. Like if I have for example, let me show you with a rough sketch here. If I have member like this, okay. Sometimes this writing pad doesn't work in classroom, so still I'm not offering you full-fledged classroom in the session in the classroom, because bandwidth and other issues are there. But suppose this is a truss which is loaded like this. If I ask you to solve this with the help of ordinary method of joints or method of section, you probably may not be able to analyze, because this is, you can see that this truss is externally determinate but internally indeterminate by 1 degree, because you have an additional member right here. So what is the solution? Like, can energy principle somehow can be utilized for this solution? So the answer is of course yes. You can use the total energy stored in the members due to the forces, and you can utilize those energy values by taking partial derivative of the total energy stored with respect to the causing forces, and then eventually you can obtain your reactions, your internal forces also. So for example, if I write that summation of all the forces and the partial derivative of that forces with respect to the force, particular force of the member, right? And if you multiply it with L upon E, that is the property that of the member, definitely it is always, this is the amount of total energy stored in the member and should be always minimum, and minimum is always zero. So using this concept, we can definitely obtain the force in a particular member itself. I'm going to show you how we can do it. But before that, let's have a hands-on practice on one bent cantilever, and if possible, we'll go for one variety of the moment of inertia in a beam also. Right. So after having sufficient practice on these two varieties which were pending, then we'll take up one numerical of the truss analysis like that. So, friends, it is very much necessary for you to keep practicing the variety of the numericals at your own, on your own. Right. So, let me give you, as I said, today I'm not going to work extraordinarily, I'm not going to work continuously. You have to tell me and tally the answers. Right. All right. So, let's go for a first practice numerical. Right. Example 1. Okay. All right. So let me draw first of all the bent cantilever itself. Right. Assume that this is a straight line. Right. All right. Then we have a bent cantilever. This is a numerical from your reference book, which I am taking for practice of all of you. Right. And where you need to utilize your old learning concepts. Here you can see it is a kind of prop cantilever which is indeterminate, right? It is not a determinate structure. This is not deflected one. Let me try to refine it. Okay, looks great. This is let's say uh, 2 meter. This is again 2 meter itself, and that's also 2 meter distance. And here you may have, let us say, name of this ends. Please write down all this in your notes. I'm not going to start it, you have to start it. This is A point, this is B point, let's say this is C point. I have selected this, as I said, it is a solved numerical from your reference book, but just for your practice, because I'm sure that many of you may not be possessing this solution with you, so that it's nothing wrong to carry on with this practice also. And however, I'll be asking you one by one at different stages, right? So what is, let us start the solution. Our intention is to find reaction at point B. Now, why we are taking this solved numerical is, once you are showing your capabilities and skills to solve this kind of ordinary problem, then I may go for some complex problems like this portion is loaded with UDL, some horizontal forces are there in addition, and then you can make this in a complex format. But right now it is very simple, right? So it is just an ordinary indeterminate structure with how many degrees of SI? What is the SI of this structure? Anyone? You can raise your hand. What is it indeterminate or determinate? And if it is indeterminate, what is the SI of this system? Anyone? Anyone would like to raise the hand? My question is very simple. Is it determinate or indeterminate structure? Let me select randomly. And don't tell me that your mic is not working. Right? I know that all of you are having good gadgets and mics are working well. So if you don't know the answer, that is fine, but at least answer the question, right? So I'm randomly selecting, like, let me select Neet Kalavadia. Okay, so Neet, please unmute yourself. Are you there? It shows that you are there. So just unmute yourself, Neet. If it is, if you don't know the answer, don't worry. Please understand. I'm not going to punish anyone, and it's completely fine. If you don't know what is the answer, I can understand. But I just want you to speak up, right? At least tell me the yes or no, like whether this structure is determinate or not. That is a very simple question. Neat. I have already asked you to unmute yourself. Roll number 5005. Neet Kalavadia. Are you there? If you are there, just you can raise your hand also. Say like yes, sir, in the classroom. We have got one hand here, hand raised. Birendra, I know you are there, you know the answer, but I want to ask you, I mean, ask somebody else who can answer, who can interact with us, right? We'll come back to you in case if Neet is not responding in that case. So let's wait for a few minutes. I know the standard answerers from the classrooms, those who are always answering, but there should be a chance given to everybody, right? And why not to give chance to somebody who is not active in the class so far? So Neet Kalavadia, we are still waiting for you, boss. At least you can unmute yourself and say you know or don't know, whatever. I just listen to your voice. So unmute yourself, Neet. So if you remain inactive, it will be difficult for me to give you an attendance. Right? This is not a right way, attending the lecture. At least you should say, I don't know, sir. Whatever is the answer. many others are answering this question in the chat box. I can see. Right. This is okay. That is good. I understand. But what about our Mr. Neat? Please tell us what is your answer. I'm interested in that. So this is not done, boss. You have to answer. Would you like to write in a chat box? I'm still okay with that because I have opened the chat box also. So if you wish, Neat, you can write down your answer in chat box also. That's completely fine. You can respond over there. Okay, all right. So let me take your number for a while. Right. Somebody's writing. Indeterminate structure. That's what you have responded, I think, Neat. Okay. So you are right. Then why you are not unmuting yourself? Okay. So that's fine. That's okay. You are right that it is indeterminate structure. So thank you for responding in the chat box at least. So by what degree? Now the next question goes to Happy Getia. Is it, if it is indeterminate structure, what is the degree of indeterminacy? Happy. I have allowed you to unmute yourself. Happy is saying yes, sir, but what is the degree? 1 degree? Okay. You have written it 1 degree, that's fine. All right. Fine. So I understand sometimes you are in a condition or a situation where the background voice may be a problem. So I'm giving you that benefit of doubt, like batsman gets benefit of doubt many a times. So the same doubt, benefit of doubt, I'm allowing you. That's fine. I don't mind. Just enjoy the class. That's it. That's it. I'm not pressurizing anyone. So please understand it should be a happy environment, happy learning. So if you don't know, frankly, you can say that, sir, I'm still not confident. That is perfectly fine for me. If you know the answer, you can happily unmute yourself if you are in an environment where it's not disturbing the class. Okay. So fine. So now all people get ready because we have got our answers that it is indeterminate structure by 1 degree in terms of statistical indeterminacy, and naturally we shall be selecting our reaction. Yes, reaction at B. So we are interested to find point B. That means it is reaction at B. Okay, now everything is known to you. What you have to do, you already know. So please start and give me the first equation. Sorry, the first step is the separation, like development of the table, right? That is our first step. So who will tell me, like, how should I give the divisions? Dipesh. Yes, Dipesh. How should we take divisions? I mean regions or limits in this structure? Or anyone else would like to help me to write the segments in this structure? How should we start? If Dipesh is not responding, anyone else can respond. Raise your hand and unmute
DC
yourself.
first, sir.
Yes, Dipesh.
DC first.
I'm not getting your voice, dear, but I think you said that D2C like that, but that's fine. So the first division is naturally D2C, where we can keep D is the origin, of course, and its length is 0 to 2 meters. You have to teach me now this time, right? So you will be telling me and I'll be progressing in the numerical. So now 0 to 2. So I need a moment equation because rest of the things are very simple, and I can understand somebody is writing in the chat box, but I prefer that you raise your hand and we can talk in the classroom. So assume that you are in a classroom, boss. Why are writing and wasting your time in that? Instead of that, you can raise your hand, I will unmute yourself and we can have some chatting, right? Since last many days we have not been talking to each other, so it's a good platform to even talk to each other. So now I need an answer of mx, and who will answer me? Raise your hand, or should I randomly select? Right, you decide. Can I have a hand raise in this? Or let me go to Mangal. Mangal, are you there? I think you are there, so would you like to unmute yourself first?
Yes, sir.
Yes, very good. Excellent. Thank you, Mangal. So you raised my confidence level. Okay. Now you tell me what should I write here as a moment equation for this particular region D2C?
G2C, sir.
Think about it. Think about it. See, I'm standing here. Let me explain. I'm
X,
standing here somewhere,
X,
and
yes.
this is X. So this distance
Yeah.
is X, and you have a force. So come on.
Minus
Minus
20, 20,
minus 20
X,
X.
bracket,
That's all. That's it. That's all. That's it. Yes. And now, what should be dmx upon dvb? Can you think of it?
0, sir.
Yes.
0.
Zero. Yes. So Mangal, you made the day. So thank you for sharing your understanding with all of us, and now you can mute yourself. I would like to go ahead with another segment, C2B. This is what I want, dear students. This is what I want from your class, that you should be very outstandingly active. See, there is nothing in this numerical which is very difficult, right? The only thing is how you take it further, how spontaneously you are responding. That is important. All right, so now I need answer of this moment equation for segment CB from, let me check. I would ask to, uh, I will go down, slide down the names of the students. I can see all of you. That is good. Hey, somebody has left the class. This is not done. Don't do it. Uh, don't do it. Let me go down further a bit. Dharmesh, Dharmesh Chawda. Dharmesh ji, please tell us what should I write in this equation. I have allowed you to unmute yourself. Yes, Dharmesh, are you there? If you are there, just say yes, sir. At least unmute yourself. And if you don't know, I'll explain you how to do it. But at least you come into the front, and now what you have to do is you have to slide down x like this, and you have to think of the equation for this moment. See, this is what is lagging. Like if I keep on doing the numericals on and on and on in this digital platform, and if you are not involving yourself, or if you are not practicing sufficiently, there is no point of learning anything, and it doesn't reflect the actual learning. So I'm again allowing you to unmute yourself. Dharmesh, I have unmuted yourself. You can unmute yourself from your end. Once again, I'm doing the same thing. Okay, let me go to Darsha. Unmute yourself.
Yes, sir.
Yes, so what should be the equation here for
Sir,
port? Minus 20
minus 20 into 2 plus
into
x plus 2.
x plus 2. Why you are suggesting x plus 2? See, let me explain. This is for everyone interest. This is our original segment. I have started my x from here. Now this is my x. So this is 0 for me and this is 2 for me. Now my force is somewhere here and it is at a distance of 2 meters. So if I take this 20 kilonewton, what would be my moment here? It will be 20 into 2. That's it. Now it becomes externally added moment. So there is no further addition or there is no need to further extend this, consider this x. It is, this answer is valid for entire length 0 to 2 meter. Got the point, Darsha?
Yes, sir.
So 20 into 2, that is our equation, isn't it?
Yes, sir.
Okay, so naturally the answer of this is 0. So on your behalf, I'm writing that 0 itself. And now I will clean up this portion so that we can write down our last segment, and that is B2A. Okay, friends, I'm giving you a hint. B is there. B is the origin, 0 to 2 meters. Now please tell me the equation. So I will go with Mr. Ravi Kanjia, Kanijia. Okay. So, dear Ravi, unmute yourself.
Yes, yes, sir.
Yes, very good. I like this. I like this. Okay, you just can you tell us how we can write the equation according to you, whatever, let it be, right? You can go on with you.
We be into X.
VB into X, excellent, excellent. Anything else, dear? Anything else? This is right. This is
No,
perfect. Hmm. Try it. Would you like to consider this gentleman 20 into 22? Should you think, do you think that it should be included or not? I mean, it's up to you. You can say yes or no. Then I will explain. Uh, should you consider this 20 into 2 along with this VB into X?
mm, yes, sir.
Yes, that's it. So that was the missing component. So I will happily add over here 20 into 2, that is 40. So this is plus because this, okay, thank you, Ravi. And now let me explain why this 40 should come here and why this is positive, because if I further magnify this, this is our continuous segment C, B and A. Okay, and here this person known as VB is waiting for us, and now we are starting from 0 to 2 meters, right? So it will be creating, yes, anti-clockwise moment here, so that's why it is positive in this case, while here this gentleman called 40 is already waiting for us, right? And this is very much applicable to this next segment also. You can recall we used to do this in the cantilever portion, if this is something like that and if this force is here, and when you enter into this segment, if this is the force, then what we used to write is 20 into, let us say this is 2 meter, so 2 plus x. How can we forget this, right? So that's the same story here being repeated. The only thing is it is applied moment, that's all. So applied moment is applicable for 0 to 2 meter again, 0 to 2 meter again to any of the length without any addition of the distance. And that is why we have to include it. And since it is clockwise, it is minus, this is anti-clockwise, and that is positive. Okay, so that's the only point which I was interested in to know from your side. Now, with the help of all our friends, our student friends, we have resolved this major task, right? And definitely, I would, when I would take del mx upon del vb, I will be having answer like x for this segment. So now, friends, it's very simple for all of us. So how we can write down delta u, or we can say when you take the du upon dvb, it should be 0, it should be always minimum, so that's why 0 we are writing here. And with that, can we add them up together like 0 to 2? Okay, we'll write down the first, obviously we will take 1 upon ei as constant outside. So 0 to 2 meters, the first is minus 20 into x into 0, of course, into dx plus 1 upon ei. Now you should be doing it parallel with me, minus 20 into 2 into 0 dx, of course, and plus 1 upon ei, 0 to 2 meters, of course, vb into x minus 40 into x dx. So we have only active hero of our work is this, because this goes in a drain, so it becomes 0 over here, right? So can you see that how simple it is to use the energy principle number 2 for any complex type of problem? Yeah, by looking it looks little complex, isn't it? You have a support and you have a bent cantilever, and by looking it is very dangerous in a way, right? But it is very simple if you use energy principle number 2 in that case. So now I'm confident that if I give you little more complex solution, you can definitely work upon it like this, right? Anyways, you just tell me the final answer. Now I'm leaving up to you. What is the answer for VB that now you have to give me, because simplification of this equation is very simple. Like if I take EI constant here somewhere, and if I directly multiply this VB into x square minus 40x, and then if I take integration afterwards, still it is simplified view. Pardon me, I'm writing in this area. Here you just need to take it further, like 1 upon ei. Here VB would be, I mean, we are equating this with 0. So it is now it's the right time to take integration here. So I'll directly write down that portion, only integrated portion, VB x cubed upon 3 minus, I know I'm doing little shabby work today, but it's more live. So it gives you a kind of pleasure to work with it. So it is 0. So VB 2 cube upon 3 minus 40, 2 square by 2. So what should be the answer now? This is equivalent to 0 basically. So give me the value of VB clearly. Let me see who raises the hand. Raise your hand now. You can feel free to raise your hand. It's very simple mathematics only. Any one of you can respond to this value of VB based on this equation, this one. Birendra with us. Yes, Birendra.
Sir, I am getting 30 kilonewton.
Very good. It is perfect. So that is 30 kilonewton. That's the reaction. Okay, Birendra, thank you. And now we are almost done. We can rewrite our condition of problem in a different way like this. Since we have solved it, this is 20 kilonewton. Okay, friends. This is, however, it was naturally it was a simple numerical, but this is 30 kilo, sorry, this is 30 kilonewton. So I will write down 30 kilonewton here. Now what other thing we should expect? We have some more reactions, you know, to get. So if you work upon with sigma v, sigma m, sigma h, rather I am interested to find out ma, va, and let us say ha. In addition, we can calculate MB also, MC also, because we know that MD is 0. So now who will tell me what is the value of MC? Very quickly. Obviously, you know the distances 2 meter, 2 meter and 2 meters. MC. Okay, let me help you. 20 into 2, that's it. And it is clockwise, so it is negative. That's it. Kilonewton into meter. MB. Sorry, here it would be 20 to 2, that is 40. Sorry. So 40. And this doesn't change here. See, this is the force, this is the distance, so it will create 40 here. So that is MC is 40. Let me change the color. So this 40 kilonewton is the applied moment, becomes MC value. Also, it becomes MB value as well, because till here, when you reach above this level, it is still existing in this member. So it will be 40 here again, minus 40 kilonewton into meters. Now we have reached at MA, friends. So what should be the MA value now? Who will tell me? I need an answer for MA. Unmute yourself, any one of you. Become a volunteer. Raise your hand. I'm here to unmute. It's very simple. I would say manually you can calculate. You don't even need a calculator at all. It's that simple. It's too simple. Yes, Birendra again. Yes, Birendra.
Sir, I think minus 10 kilonewton meter.
Uh, okay, minus 10 maybe one answer. So I'm registering your answer for a while because I doubt about it. So let's see somebody else if answers to this, and then you can compare your answer. Anyone else? I'll be waiting for any other answer. It's very simple here. Okay, Prashant has raised the hand. So yes, Prashant, you
So
can
30 into 2 minus 40.
yes. So see, in this portion you can see that from B to A there are two moments working together. One is 13 to 2 and second is 40, which is already existing over there. So you need to consider it, and with its numerical sign also, it is clockwise, so negative. The 13 to 2 becomes anti-clockwise, positive. So you can go over there and go for this calculation. 30 into 2. So Virendra, I think will reconsider your answer and you have to revise it. So it is answer is 20 kilonewton into meter. That is final answer here. All right. So I'm I think all of you are comfortable with this, and you can mute yourself now, Prashant. And based on that, you can again go for development of the variety of the diagrams. However, I will not go for it right now because I want to give you, as I said earlier, I want to give you a numerical with varying moment of inertia numerical as well, so that we can complete all the patterns also all together, right? Now we want to calculate friction moments uh, in a beam. So let me give you that problem statement. So this is another problem statement like this. Right. Or if you wish, you can go through this diagram as well as a sense of completeness. Before we go for it, let me show you how to draw it. So here you have point A. I'm just demonstrating it how to do it. Just give me a moment. Okay, friends. So A, and this is B here somewhere. This is C, and let us say this is D. Now you know that 20 kilonewton, that is anti-clockwise moment. So we'll consider it on the, and it will be creating hogging of this member. So hogging we take inside of this diagram, and sagging will be taking outside of this diagram, so that also we continue with our basic understanding. Here MB is 40 and it is also clockwise, right? So it is creating sagging of this portion, right? Actually this is the hogging of the portion, this is sagging. So here I would, once I have shown hogging on this side, so naturally I will be showing sagging on the other side. I thought that why not to complete it properly, so that you can also get an idea how to draw BM diagram for that condition also. So let us say this is 20 for 2, so 40 for 3, which is quite logical. Okay, on the other side now we have MCs. Now this moment remains continuous, so till here there is no variation, so it is still 40. And on this side again it is creating a kind of deformation like this. So again I will continue to draw it above the line itself, and it eventually becomes 0 here. So this is the BM diagram, and now we need to join them together like this. So this is the hogging portion, and this is sagging portion, this is also sagging portion. So likewise, you can again go for the shear force diagram as well. Bending moment diagram is completed here, right? So, I mean, if you have right answers in terms of signages, you can definitely go with, and always stick to your fundamentals of the signages. Like hogging is shown below the line and sagging is shown above the line. In the diagrams of the bending moment, you already know that. So that is how we have shown it, right? All right. So now you please register this question in your notes. Okay, and here you can register yourself. So now let me give you a problem statement. Here it is, let's say a portion. Okay, this is 3i, and I'll be reducing it up to 1i, right? I only. I'm changing the data from your reference book so that you can additionally, because sooner and later you will be having your registered, I mean the textbook, so should not be a repetition. A, B, and this is something called C. Okay, here. Now, since this is 3i, this is I, let me change the data for length also. In your reference book, it is 1, so I'll be going for at least 2 meters. And here it is double of that, so it would be 4 meter. Okay, friends. So amazingly, we have changed the data. In that book, we have 9 kilonewton force here. So I'll be going for, let us say, 20 kilonewton. Okay. So what is our ultimate aim? Our ultimate aim is to find out the friction moments at A and at B, what it should be. Now we'll be using the minimum strain energy principle, or that is say second energy principle by Castigliano. We have a clear cut distinction of the moment of inertia value, so that you have to register in your mind and you have to keep it with you. And we shall be starting by taking the redundants. First of all, you have to identify the redundant. So who will tell me what is the degree of redundancy in this, or SI? Any one of you? Supposing avoiding the horizontal conditions, I mean sigma h, if we avoid, then even though we have, what is the degree of redundancy? That means how many unknown quantities which are to be required to be calculated. Actually, we know that these two moments are themselves are the SI value, degree of indeterminacy. So redundants are moment at A and moment at B. That means fixed moment at A and fixed moment at B are the redundants. So 2 degrees of SI are present in this problem, right? So we need to find out one by one of them. So as usual, first we will be taking the redundants one by one, in case like at one end we will keep fixed and the other end will keep it free, right? So these are the obvious redundants that we can practice. Now that is up to a choice of yours, right? If I want to, there are two options. Let me explain very quickly. Like if I want to make this structure determinate, what are the obvious things? This is one thing which you can think of, and these are considered as redundant 1 and redundant 2. In the opinion 2 or option 2, you can go for this solution, right? Like I just remove it on one side only, so it's like this. So this is redundant 1 and this is redundant 2. So to keep it simple and very familiar equation, we can develop 0 to x and then we can go to 0 to x. Otherwise, what happens in the case of simply supported beam, you can start from one end, it is 0 to x here, and other end 0 to x here, right? That is also valid and possible. But in that case, you have to first of all obtain the reactions also. Then only you can start the other calculations. While here it is not at all required. So this is more faster, flexible. So we shall be going with that by considering the redundance as reaction, right, at VB as the reaction, and MB as the redundant, right? So that would be our primary lookout, right? And you should also go for on this side as well, right? So should not be a problem. So it is up to your choice. So in my opinion, you can start from left hand side also, or you can go for right hand side as well. So any one of you can select either of these sections, or even though you can go for this solution. I'm not forcing you to follow a particular pattern, but I wish that all of you should complete this numerical at your end by default, right? Because since you have experienced recent just now that it was very difficult for many of us, still even after this repeated practices, you are still struggling to answer the basic questions in this problem, which I have observed, right? Which is not a good sign, and which I don't want also. I don't want to rush for the contents. I want every one of you to take your enough time to understand the very basic steps, right? So in this case, if new numerical, which just now I have suggested, you can start your numerical with, let us say this is a cantilever, this is, let's say, VB, and let us say this is not clockwise but anti-clockwise, it should be up, so that means it is NB. These are my redundant quantities, and here I can apply a force of 20 kilonewton. This is 2 meter, this is 4 meter, this is 3I, and this is I. Okay, this is I value only. Okay, friends, so with this simplified format, I insist that you select one by one of them and start writing the equations. So I will help you for initial development of the equation A, B, and C. So let me write down the segments. B to C, length is, origin is B here, length is 0 to 4 meter. I will write down the equation. Now VB is there, so we are starting with our X here. This is the X. So I'm standing here right now. So if I multiply VB into X, so that will be my simple equation for moment, and it will be naturally, anti-clockwise. So I'll be writing VB into X, and of course the MB is clockwise, which we cannot forget, so we'll write down MB also. That is my equation for the moment over here, generalized equation, right? MX. Now one care should be taken that one by one we have to take partial derivative of this MX. First we'll take it with respect to VB, so in that case it is X, and del mx upon del mb, right? So it will be 1 in that case, negative 1 in that case. Is it fine? It's very simple to understand. So from C to A, I wish every one of us should note down all this, 0 to 2 meters. Where this 3I and I will come into picture? When you note down the total of this deformation, at that time it will come into the picture. Now here, let's start with C, VB into, now we are here, this is your X. Okay, so how do we write it in that way? Anyone would like to give inputs over here? Any one of you? How should I write VB? Yes, usually VB into, yes, 4 plus X. Is it okay? Right. Then minus MB, and of course this is clockwise, so minus 20x, right? So now del mx upon VB, that is going to be 4 plus x, that's it, and here it is again minus 1. So friends, I have made you bring you in the comfort zone of yours. Now you can simply write the equation one by one, right? For delta, you can take deflection del u upon del v b equals to 0 first of all. So 1 upon EI, let's put them down together, 0.024, right? So del M, I mean mx into del mx upon del VB, so it is like that, VB into x minus MB, right, into x, that is dx plus 1 upon 3 EI, right? That you should directly include over here so that you don't make any mistake. Now VB into 4 plus x minus MB minus 20 into 4 plus x dx. When you simplify this, you will be getting one equation which includes VB and MB. And when you will be writing du upon dmb, you will be also getting another equation. I am just giving you overall solution. Detailed work you have to work out. VB x minus MB into minus 1 dx plus 0 to 2, right? 1 upon 3 EI, don't forget that, 1 upon 3 EI. Then you have VB into 4 plus x minus MB minus 20x into minus 1 dx, and that's it. So equate 1 and 2, resolve them by elimination method. You will have some equation number 1 and 2 carrying the values of VB and MB. So eliminate either of them and obtain your reactions. That's it. And then you can carry on with the first principle of calculation of reactions and you'll be getting your answers. So friends, I would stop here. It was a nice interaction with you today on online platform. This is what I want. If you are right or wrong, that completely doesn't matter, but it is important to communicate with each other. So I appreciate and I'm happy that you have started interacting with me. So we'll keep on doing this kind of exercises in future. Tomorrow again, I will, before we begin the trust analysis, I would like to listen from you. I will not solve this for you. You have to directly give me the answers. So I'll be looking forward for your answers tomorrow. And then we will start trust analysis by applying second principle of energy. And then we'll go for some other variety of numerical. So thank you very much for joining today's class. And I'm sure that most of you have already entered your details in the chat box so that I can take your attendance, right? If not, please start entering your details in the chat box earlier if you have not done it, so that I can register your attendance from there. Probably this time you have forgot it, so I'm giving you one more minute. I'm not stopping the session, and so that allowing you to enter your details in the chat box. Don't worry, enter your details in the chat box if you have not done earlier, and I'll wait for next 2 minutes and then I will close the session. So thank you all. Those who have entered detail, they can rush to the next session. And thank you all for joining this session. We'll meet tomorrow, right? Tomorrow class is there, so we'll meet over there. Thank you all. So I'm stopping my sharing here, but you can still enter your details if you wish in the chat box. And then after exactly 2 minutes from now, I will end the session. But it seems that most of you have already entered the details, so it's good, right? Good morning. 2040 pass out of course. Give me a second. So thank you all for joining this session, and I'll be more than happy to meet you in the next class.